Everyone. Yeah, so as I said, just say hello in the chat. It'll be sort of an informal attendance and just to make conversation. What's a favorite childhood snack or something? Oh, yeah, shortbread cookies, absolutely. What's a spritz cookie? I'm curious. Hey everyone, for those of you coming in late, we're just saying hi in the chat and talking about our favorite childhood treats. Oh, there's a battle going on now. Okay. All right, we have about 20 people. uh, okay, so before the flame war gets out of control, I guess we'll start. So we've been talking about we've been talking in chapter 8 about Kepler's laws, and now we're moving on to coupled oscillators. So the plan for today is I'll just do a little mini lecture getting us a little bit into chapter 11, and then we'll break to continue working on the worksheet that I sent out last time. Yeah, basically that's that.
I had a quick question.
Oh yeah, sure.
I think you mentioned last week something about wanting to see part of the paper, but I can't remember exactly what you said.
Oh yes, it was just an informal suggestion that if you have a section ready that you either email it to me or share it via Google Docs or something, just so that hopefully you're on track and like not leaving everything to the last moment. Also, that reminded me actually. So people have been reaching out to me about well, difficulties of collaborating on this type of project, given that we're all separated like this. So I'm going to be I'll put a link on Moodle, which will go to Google Forms survey, listing possibilities in terms of what adjustments we can make to make things easier vis-a-vis the paper and video. And so you can select more than one option, and I'll take all that into account, and we'll see what works best for the most number of people. Sound good? All right. All right, so I'll send that out once we get onto the worksheet. Yeah, just with or without the scale. All right, but for now, we'll continue. We'll start off on chapter 11. So chapter 5, which we skipped over, was about oscillations. Chapter 11 is when you have more than one oscillator and they are actually coupled to each other and influence each other. And you would have probably seen some of this talk about normal modes in waves and oscillations. So hopefully it won't be a completely new topic for some of you. But even if you haven't, even if you have seen it before, well, I mean, we still get some new tools here because we'll be taking a bit of a matrix approach, but also a bit of a Lagrangian approach eventually, and looking at coupled oscillators in a few different ways. All right. So our starting system to kind of get used to the ideas here is going to be two masses connected to three springs. So we have two walls, we have spring, mass, spring, mass,
Dr.
spring.
Paily, your video's kind of blurred. Can you
Oh,
check the
yes.
focus, please? Thank you.
There we go. All right. Right. So we'll make life simple and say that they're identical masses. But as for the spring constants, we will say, okay, these two springs have the same spring constant. But this one we'll say has, we'll kind of keep it general and call it just K2 right now. And we'll examine a few special cases, one where K2 is actually equal to K and one where it's not. Yeah, so we'll look at that. So there are, of course, a lot of possibilities here. It could be that in the equilibrium setup that all three of these springs are stretched when they are, just stationary and relaxed, not relaxed, but when the masses are stationary and in equilibrium. It could be that all the springs are stretched. It could be that all the springs are compressed, but balancing each other off like that. But for simplicity, we'll assume that at this moment when they are all stationary like this, that they are all relaxed at their natural lengths. And it turns out it won't actually make a difference as far as our analysis goes. So this would be the x1 equals 0 position. This would be x2 equals 0. So we'll have x1 increasing this way, x2 increasing this way. So if x1 is 0, then it's in the natural equilibrium position, and same for x2. But then if it moves this way, we can see that this middle spring is going to start being compressed, and this spring over here will start being stretched. All right, so we can write, well, Newton's laws for each of these masses. So let's say that each of them has been displaced a little bit. And for convenience, we'll say it's to the right. Right, so the second mass has been moved some distance x2. First mass has been moved some distance x1. Oh, that's a spring here. It's K2, yes, all right. So if we look at the first mass, what do we see? We see that it's experiencing forces from both springs. So let's take them both into account. So we'll have mx1 double dot is equal to, so we have the force from this spring. And what's that going to be? It's going to be, since it's being stretched, it's going to be in the negative x direction. So it's going to be minus k x1. Right? X1 here represents how much it has been stretched from the equilibrium position. So that's one of the forces. What about the force from this spring? Well, how much has it been stretched or compressed? Let's sort of take the easy case. If x2 was 0, right? If this second mass hadn't moved at all, so that the only one moving was this first mass, then we could see that this spring. Is there a question? Oh, okay. question? No. Okay. So the change in this spring would have been basically minus x1. On the other hand, because the second mass does move, what we end up with is actually x2 minus x1. And that is, let's see. Right. So plus k2 x2 minus x1. So we can check signs here by looking at the limiting cases. So if x2 is 0, then we know that this spring is being compressed, and so the force will be in the negative x direction. So right, if x2 is 0, we'll have minus k2 x1. That makes sense. If, on the other hand, x1 is 0 and x2 is non-zero, then we know that this spring is being stretched, and so the force will be in the positive x direction. And that makes sense again with the signs that we have chosen over here. So any questions about this expression for, this is just F net equals ma, focusing on just the first mass here. All right, no questions? Okay. All right, so then let's look at the second mass. So similar thing plays out with the second mass. So we have mx2, oops, double dot, and there we go. Right. What we end up with over there, right, we'll have k2 x, sorry, k2 x1 minus x2, and then we'll have minus k x2. There we go. All right. So again, let's double check that this makes sense. So this term would come from this third spring over here. So if x2 is positive, then this spring is being compressed and the force will be in the negative x direction. So that makes sense. How about for the k2? If x1 is 0 and x2 is positive, then this spring is being stretched, and so the force will be in the negative x direction. So that's if x1 is 0 and x2 is positive. X1 is 0, yes, it gives us a force in the negative x direction. And similarly, if x2 is 0 and x1 is positive, we know that this spring is being compressed, and so there'll be a force in the positive x direction. Okay, so we have these two equations, and what we're going to do is group them up according to x1 and x2. So these equations are going to become, so we'll have m x1 double dot. If I group the x1 terms together, what do I have? I'll have minus k x1 and then minus k2 x1. Okay, so minus k plus k2 x1 plus k2 x2. All right, and then similarly x2 double dot, I'll have something times x1, something times x2. So for x1, I have only one term here, is just k2. And for x2, I'll have minus k2 minus k. So I'll put a minus k2 plus k x2. All right. And what we'll do then is rewrite this in matrix form. So over here, I can write this as this, right? So if I do matrix multiplication here, I have m times x1 double dot plus 0 times x2 double dot. Okay, so that first entry on top will be just m x1 double dot. And on the bottom row, if I do row and column, I'll get 0 plus m times x2 double dot, which is indeed the second entry over there. All right, let me do something similar over here. So I'm going to write it as a square matrix times a column matrix. Just looking at the coefficients, I see that this is K2, this is minus K plus K2, this is K2, this is minus K plus K2. Okay, and if I just want to label each of these, so each of these is a matrix, right? So this is a square matrix, this is a column vector. But if I want to just label them stuff, I could write it like this. Right, so the x here represents this column vector of x1 and x2. And if I pull out a minus sign, then what I get here for the square matrix is going to be k. And then the mass one is just this diagonal matrix here. Any questions so far? All right, so well, obviously writing it this way, we're making a very obvious callback to just the plain simple harmonic oscillator, except now it's in matrix form, okay? So we'd expect that each one of these, x1 as a function of time and x2 as a function of time, is going to be something like the usual x of t is a cosine omega t plus some phi naught. We expect a solution along those lines. It turns out to make life easier, what we're going to do is we are going to look at a solution. We're going to allow a complex number solution, because that way we don't have to worry about switching between sines and cosines all that much while we're doing derivatives. We can just do derivatives of exponentials, which are much easier. At the end of solving the problem, we will just take the real part of that complex number, and that's going to be a solution to our equation. So what we will have is, let's see, yes. So yeah, we're going to assume that, so this would be Z1. Z1 instead of X1, we're going to use Z1. There's going to be a similar Z2. And those are, we expect, going to be our solutions. So what will that look like? All right, I'm going to flip the page. Any last questions before? No? Okay. So let me just re-emphasize some of the stuff over here. Is that K? Remember, we've extracted out the minus sign. So this will be K plus K2 minus K2 minus K2, K plus K2. Okay, and so our guess so now we'll write a Z column vector, and that is going to be basically A1, A2 times e to the I omega t. So I've pulled out e to the I omega t as a common factor, but we see that we have different complex amplitudes. Right. So yeah, so let me just emphasize that here. A1 and A2 belong to complex numbers. Right. And so again, I can just write this as some A times e to the I omega t, where A is going to be a shorthand for A1, A2. All right. Well, if this is my Z, then what is my Z double dot? I'm going to end up pulling down a factor of I omega each time I take a derivative. So I'm going to get minus omega squared times A1, A2, e to the I omega t, right? A1 and A2 are complex, but they're constant, so they don't do anything with the time derivative. So this is just minus omega squared z. All right, so let me take these results and go back to the equation I had. So the equation I had, once I generalized it to complex matrices, was of this form. And I'm going to plug in for z. So I'll have minus omega squared m z is equal to minus kz. But then we said that, z can be written as just a times e to the I omega t. Okay. And let's just pull all this to one side. So what do we have then? We have k minus omega squared m, and this will be a square matrix, times a times e to the I omega t is equal to 0. Okay, so so let's remember that sure, this is just a numerical factor, so, and it's basically non-zero, so we can just divide that out, that's fine. So then we have this square matrix of k minus omega squared m times this column vector A is giving us 0. All right, so now let's think a little 2x2 matrices, linear algebra type thing. Well, let's call this, sure, let's just call this B, I guess. All right, so we have some square matrix B, and that acting on column vector A is going to give us 0. Now, there are two possible cases that we can divide this into. B is a square matrix. Either its determinant is 0 or it is non-zero. So if the determinant of B is non-zero, then one of the properties of a square matrix is if its determinant is non-zero, we can define an inverse matrix, right? So if determinant of B is non-zero, oh dear, internet. Okay, but back online now, hopefully. All right. Yes. Okay. So if the determinant of B is non-zero, then we can define a B inverse. And so we could just multiply both sides by B inverse. And what we would end up with is just A equals 0, which is a boring solution. That tells us that the two masses just stay where they are and nothing happens, which is, yes, a solution, but a boring one. Right. So the more interesting case is if the determinant of B is 0, then we can't take an inverse, right? But we still have this matrix equation which needs to be satisfied. And so we can have non-zero values for A that will satisfy this equation. So let me just recap that on the next page, and feel free to ask questions. So BA is equal to 0. So the two cases are if determinant B is not 0, then B inverse exists. And so we can do, oh, B inverse times BA is equal to B inverse times 0, but anything times 0 is 0. So we just get A is equal to 0. So it's like true but boring. If determinant B is equal to 0, B inverse doesn't, whoops, B inverse does not exist. A has what we call non-trivial solutions. All right, so we see that the interesting stuff happens if the determinant of B is 0. So let's run with that. Let's see what that tells us. So we will, what do we want to do? Yeah, okay. So we have K, so determinant of K minus omega squared M. Determinant is 0. And let's write what that is. So K is K plus K2, and then minus K2, minus K2, K plus K2. And then we have minus omega squared times M, but M itself was just a diagonal matrix, so it's just omega squared M, 0, 0. So this, right now we're just doing the matrix, and then we'll take the determinant afterward. So we have K plus K2 minus M omega squared. We have minus K2. We have minus K2. We have K plus K2. Sorry, that is a plus over there. Minus M omega squared. All right, and now take the determinant. So this is our matrix B, right? So determinant B is going to be, well, this two terms multiplied minus the product of these two terms. So that, luckily for us, in this case, very symmetric. So we can easily do that. So this, the whole squared minus K2 squared. And what we want is for this to be 0. Questions so far? Okay. All right, so let's run with this. It's going to be a little bit messy. What do we have? We have, right, K squared plus K2 squared plus M squared omega to the 4th. And then we'll have plus 2k k2 minus 2k2 m omega squared minus 2k m omega squared and then minus k2 squared is equal to 0. Okay, so right now this general case will be a little bit messy, so let's actually simplify it to an even more symmetric situation. Yeah, 1 second. Well, no, okay, let's run with this a little bit further. So what do we have? Let me just copy it down. The k2 squared has gone away. So we have k squared plus m squared omega to the 4th plus 2k k2 minus 2k2 m omega squared minus 2k m omega squared. All of that equals 0. Okay, so this can actually be factorized. That I know is a non-trivial step. It's not obvious to me that it could be done, but it can. So let's check that this in fact gives us what we want. So first term, k squared, yes. We have a plus m squared omega to the 4th, yes. We have 2k k2, yes. We have minus 2m omega squared k2, yep. And we have, let's see. Yes, we have minus k m omega squared and another minus k m omega squared for a total of minus 2 k m omega squared. Oh, sorry, I just saw your comment, Robbie. Is this okay now or? Okay, cool. All right, so yeah, we'll come back later on to like, oh, okay, I have this type of expression. How do I factorize it? We'll get into that later. For now, we'll rest assured, hey, it can be factorized, at least in this case. And so we have this factorization. And so that gives us two solutions for omega. We either have omega squared is equal to k over m by setting this factor equals 0. Or we have omega squared is equal to k plus 2k2 over m. And so we say that there are two natural frequencies, which are, we'll call them omega 1 and omega 2. But this is for the whole system. It's not specific to like mass 1 or mass 2. There just happen to be 2. Okay, so right. And technically they're the negative roots as well, but it turns out that the negative roots give the same type of behavior as the positive roots. So we'll just focus on what's physically distinguishable. And so we have these two frequencies. All right, so fantastic, cool. We have these values of omega. What does it all mean, right? What's the physical interpretation that we can give? So I'll talk about one of the cases today, and I'll save the other one for next time. So we'll look at one I mean, this was already a special case, but we're going to specialize even further. The special case we'll consider here today is when K is just equal to K2. So it's 3 identical springs, 2 identical masses. What does the system do then? So in that case, omega 1 is still just square root of K over M, but omega 2 is now square root of 3K over M. So what do our solutions look like? Well, we haven't actually finished getting the solutions. We've gotten the special values of omega, but we need to figure out what the values of A1 and A2 in that A vector are. So let's take each of these cases. So we have when omega is equal to omega 1, our B matrix, which remember was K minus omega squared M. So now this becomes K minus omega 1 squared M. And also we have the simplification that K is equal to K2. So with that simplification, what does the matrix become? This ends up being just K times 1 minus 1 minus 1, 1. Yeah, let me elaborate on that step a little bit. So remember that our expression for B was this, right? But now we're making two simplifications. We're saying K equals K2, so this becomes 2K minus M omega squared. But then we're also evaluating at the special frequency omega equals omega 1, at which frequency M omega squared is equal to K. So you get 2K minus K is just K, right? And then this becomes minus K, this is minus K, and the same kind of thing happens here, this is just K. So if I pull out a common factor of K, I end up with what I have over here. All right, and so the equation that we want satisfied is that BA is equal to 0. So that becomes K, and then we have 1 minus 1 minus 1, 1, and then we have A1 and A2. And we want this product to be equal to 0. K is a non-zero constant, so we can actually just get rid of it. And so we have this equation for A1 and A2. So if we multiply this out, what do we get? We get 1 times A1 plus minus 1 times A2 is equal to 0. And then basically the reverse of that over here. So that just gives us a single equation, which is that A1 minus A2 is equal to 0. So we might as well just say, okay, A1 equals A2 equals just some constant A. Well, actually, hold on. Let me clarify that a little bit. I'll write that on the next page to clarify. Right now, what we have is A1 equals A2. And what we will, so we have A1 equals A2, which we'll say is, in general, A times e to the I delta. All right, what is this delta? It's just the initial phase constant. So if I go back to my z of t, right, what that was going to be was A1 times A2 times e to the I omega. And so then now that becomes A, and then here we have e to the I omega 1 t plus delta. The I is outside over here. All right. Why did I need this delta over here? Well, basically, the idea is that each individual equation of motion for x1 and x2 was a second order differential equation. So we need two basically constants of integration, right? Two initial conditions. And so A and delta are both two real constants. So that's the most general solution is of this form. Right? And so this gives us z of t. And we said that, so this is z of t, but we said that the complex number thing was just for convenience in calculation, and we're pretty much done with that now. So what is my x of t? Well, that will be our x1 of t and x2 of t, and that's going to be the real part of z of t. A is a real constant, so that's left alone. But here we have this e to the I theta, but we can use e to the I theta is cosine theta plus I sine theta, and we just want the real part. So what we end up with is x of t is a, and we have cosine omega 1 t plus delta.
Paily, I have a question.
Yeah, go for it.
What happened with the other omega term? Because
the square root 3k over m?
yeah.
Yeah, we're going to get to that.
Oh, okay. Okay, sorry.
No, that's fine. All right, so yeah, let's do exactly that. So what if now we have omega equals omega 2, which is square root 3k over m. So now what will our b simplified to? So in this case, b is going to simplify to basically k times minus 1, minus 1, minus 1, minus 1. Sorry, yeah. And again, we have that equation BA is equal to 0. So I can pull out a minus sign also as a common factor. So I'll get rid of the k, I'll get rid of the minus sign. And basically what I have is 1, 1, 1, 1 times A1, A2 is equal to 0. And we get the same equation twice, which is basically that A1 plus A2 is equal to 0. And so again, going for the general complex number solution, we'll just say A1 is equal to minus A2 is equal to A times e to the I delta. Let me clarify and call this delta 2 to avoid confusion. I'll call this delta 1. And in fact, this A need not be the same as the previous one, so I'll call that A2. Okay, so again, we just want the real part. So our x of t for this solution is going to be, we'll have A2 minus A2, and then we'll have cosine, cosine omega t plus delta 2. Okay, that's not very neatly written, but hopefully you can see what I'm going for. Okay, so both of these were solutions, and the equation of motion we had was linear in x. We never had any terms that were like x squared or x times x dot or anything like that. So that means that we should be able to apply superposition. And so the most general solution that we can get is basically the sum of these two. So we can write it as A1 that's omega 1. This is omega 2 plus delta 2.
Sorry, so where did the negative sign come on the second term, the negative 1?
This
there.
Yeah,
Yeah.
okay, so yeah, so this came from here, and this came from our condition that A1 plus A2 equals 0. So
got
A1
it.
and A2 had to be opposite. Yeah.
Okay, thank you.
So yeah, so this is our completely general solution for the equation for the motion of the system. So, I mean, okay, mathematically this all makes sense. Physically, can we have some kind of picture? Yes. So what we'll do is, so each of these solutions, right, each of these different omegas for the system, omega 1 and omega 2, they are the normal modes of the system. So let's examine each one separately. So we have omega equals omega 1. We had that A1 was equal to A2, and basically that ended up giving us that x1 of t was equal to x2 of t, right? Which we can see from this part of the solution over here. There was no difference between them. So what does that mean? It means that going back to our physical system of the two masses, it means that they were moving in sync, that they both moved to the right, they both moved to the left, and they moved the same amount. And so this spring in the middle was not stretched or compressed at all. And as a result, it had no effect on the motion, right? So they were both moving as if there was no middle spring, but in sync. And that makes sense then that omega 1 was just square root of k over m, because each of them was effectively only being influenced by a single spring. This spring was neither stretched nor compressed, so it didn't have any influence. So this was the first normal mode where they were moving in sync like that. The other normal mode, omega 2, we had 3k over m, and we were told that A1 was minus A2, and that basically x1 and x2 were negatives of each other. So that meant when one moved to the right, the other moved to the left. I'm going to draw it again, but basically when this moved this way, this would move the other way. So they would either compress the middle spring, or they would both move out and stretch the middle spring. And if we look at the effective force that each of them was seeing, what we would see there is that when they are, for example, compressing, right, the spring has been stretched by a certain amount, okay, it gives a force kx. This spring is being compressed by both sides. So it essentially will give a force of 2kx. And so the total force, and in both cases, like since this was being stretched, it was trying to pull it back. This was being compressed, trying to push it back. So they're both acting in the same direction. And so the net force on this was 3kx, which is why your frequency is basically square root of 3k over m. So we see that we have a symmetric mode of oscillation where they both kind of move together, and an anti-symmetric mode where they both move in opposite directions. And so these are the two normal modes of the system. And the most general motion is what we wrote over here, and is basically a superposition of those two normal modes. Now, because omega 1 and omega 2 are not integer multiples of each other, right? They differ by a factor of √3, and √3 is irrational. It means that the total motion, if A1 and A2 are non-zero, the total motion will not repeat. Because if one was a rational multiple of the other, then if you wait a certain number of cycles, then eventually it will repeat. But because they are one is an irrational multiple of the other, they never exactly repeat. So you get this very complicated motion, which you wouldn't, like at first glance, you wouldn't notice there's a particular pattern to it. But in fact, it's caused by the superposition of these two simple normal modes. So that's the great advantage of this type of analysis, is you start to, you no longer look at the individual masses, you start looking at the system as a whole and how it oscillates. And in fact, this is sort of the idea that goes into phonons. So those of you taking thermo might recognize that idea. Phonons are basically when you have, if you imagine a solid material as a sort of lattice of atoms connected to each other by springs, a phonon is a collective excitation of the entire system. It's a normal mode essentially of the entire system. So yeah. Questions? All right, I know that's a lot to digest, so we'll stop the lecture there. And I'll put the recording up later, and so think about it, digest it. It's all there in the textbook. I've just presented in slightly different fashion, but it's basically there in the textbook. And we will pick up on this lecture topic on next week. But for the rest of today, let's continue with the worksheet that I sent out last time. I'll also put on Moodle the link to the survey. So if you have time, take that survey. And yeah, ask me questions.